Xiaofeng, do you want to start? Or it might not be you that
We
starts?
just have a latest new one participant in the list. Welcome. So yes, I think we can begin now. You know that tomorrow is the World Earth Day, and EU, the European University Alliance, has organized the event which is called Climate Day during this special day. And as a beginning or kickoff event, we are talking about today about the water issue and its link with the energy systems and the food agriculture systems. So I'm Xiaofeng. I'm from University Paris City. I'm working on renewable energy and energy efficiency, and I'm quite honored to be accompanied by Professor Marnik Vanclooster from UCLouvain, who work on water and its link with agriculture. If you want to show quickly, Marnik.
Yes, I'm here, so thank you for inviting me to participate to this meeting.
Perfect. And then we have Professor Đorđe Čantrak from University Belgrade and the Faculty of Mechanical Engineering, a specialist in hydraulic efficiency. So he will give us more introduction about the hydraulic energy, hydropower. So if you would like to say hello to everyone, George.
Yes, thank you, Xiaofeng. I greet everybody here and thank you for being present at this lecture. I'm the head of the Department for Hydraulic Machinery and Energy Systems, University of Belgrade, Faculty of Mechanical Engineering. So I hope we shall have interesting lectures today. Thank you.
Thank you, George. See you later, very soon. So I will begin by the first part, which is what is the real problem behind water with the context of climate change, because we usually have a very dry weather today, which is linked with climate change, but we also have some flood, heavy rain issue. So these seem to be contradictory. So that is why I will try to explain the first part. What is the real problem behind water? So let's first try to see where is water on the Earth. So you know that the Earth is covered by 71% by water, but most of them, the majority of them is ocean water. So that means charged with salt. So they're not usable immediately. So what we're talking about today is about fresh water and clean water on the ground surface. And the ground surface, you have the groundwater in lakes and rivers, but you also have some glacier and ice, permanent ice in the mountains, which is not negligible in terms of a proportion. And what is more explored by people are the freshwater on the surface, which is comprised of 20% of lakes and permafrost and so on. So is this part a very small part of the clean water or fresh water that we're talking about? Because this is the main water source that we can use for agriculture and for many applications. So let's focus on this freshwater part. The freshwater comes mainly from the precipitation in the form of rain, snow, and so on. And then this is a whole cycle. You have this evapotranspiration from the sea, from the earth, from rivers, and so on. And you see that only a small percent is consumed by the industrial by industry, a huge percent that is consumed by agriculture. So it's a whole cycle. We are only using a small part of them, but the whole cycle you cannot stop evapotranspiration. So that is a natural cycle. And so when the small part is in danger, then we are. The consequence can be very severe for the society. So keeping this in mind, So what is the climate change and its link with water? If you learned a little bit about thermodynamics, so here is a Clausius Clapeyron relationship, meaning that with the same pressure, when you increase the temperature of air, then air will be able to hold more water vapor, moisture inside. So that means air is more humid in hotter weather and hotter climate. So that means due to evapotranspiration, so you will have this water vapor that accumulate in air, but with a higher temperature, you will have more water that will be accumulating in air in a huge part of the air from the vertical direction. And then you need to wait longer time until the saturation, 100% humid, then you will have rain or snow precipitation. Okay, so you need to wait longer time to have rain. So that means you have this severe dry weather problem that makes endanger agriculture and many other applications. But once you have precipitation, because you have more water in air, then you will have very heavy rain or snow. So you have this problem flooding that is linked. So this is the main message about the first part. So water is not, that the matter is conserved from thermodynamics. The total amount of water is constant. However, with the climate change, you will have this fresh water that at the right time, at the right place, that is in danger. So you have this water scarcity problem. That this is the problem that we are talking about, and the dry weather and the flooding are not at all contradictory. So that they are linked with climate change. So, and the other aspect, if we can put some physics inside, is that water vapor itself is also a big greenhouse gas. So it's even more, its effect is even higher than carbon dioxide, CO2. By the way, it's thanks to the water vapor on Earth that the average temperature of the Earth is around 300 Kelvin, so that is above zero. Otherwise, if we don't have water vapor that protects the radiative cooling, then the Earth would have been a huge glass ball. So okay, but thinking in another way, when you have more water vapor in air with the climate change, then you will have a more severe greenhouse gas effect. That means you will have even higher temperature on Earth. So this is a very bad circle effect between the water and the climate. So this is also something that can accelerate the climate change. So if I go to the next one, so you see that sea level is rising because the ice is melting on mountains. So you have more clean water that becomes saline water, so that they're not usable anymore by agriculture and the society. Except for you make the desalination of water that consumes a lot of energy or other materials. So this is the main part. And also, if we focus a little bit on Europe, there's a recent study, a German study saying that Alps mountains supply around 40% of Europe's fresh water. So because the snow will keep the water on mountains, on higher level altitude mountains during several months, so that even during summer, you still have water in the river. However, if during hot weather, the snow might disappear early before summer or during summer, and when we need water during summer, then that there is a shortage of fresh water. So the situation is quite urgent. So if go further to the whole track of water, you have sources, I said precipitation, ice, snow, and so on. And you have a storage capacity, but which is limited on Earth before the consumption, because you have storage capacity on lakes, and you have also some artificial retention basin. And you have, don't forget, you have a very big reservoir, which is the groundwater or aquifer, so that can store water during several months. So that is not negligible. But the problem is that we have overexploited groundwater aquifer that is during several months, that is the level is quite low. So we need to go deeper to have this water. And the worse, if you go deeper, the water will not be pure or fresh water, but they also have more minerals as well. So you need to make purification before the application. And then now we will talk about the consumption. That means from agriculture, which is the main part, before industry and the households. By the way, there's the urbanization, the global urbanization that makes the situation worse, because when you live in cities, you will live in high-rise buildings like this, and the roads are pavements are concrete, asphalt, and they cannot let water go in deeper in the soil, so you lose the capacity of water retention. So every rainwater should go through the rainwater pipeline. So you lose the capacity to keep water during some days or several months than the other situations. And another phenomenon that is linked with climate change is when you increase the temperature, you will have some bacteria or algae that develops very easily or exponentially. Like here, you can have this algae development, or you can also have the Legionella, which is one of the dangerous bacteria in the drinking water. So when you have this warm environment, these bacteria will colonize exponentially. So that means the fresh water is not fresh anymore. So you need to keep the quality by some artificial water treatment. So if I go to the second part, I will give the micro to Marnik, who will talk about the impact of this water scarcity on agriculture first.
Okay, thank you, Xiaofeng. So indeed, you cannot talk about climate change without talking about water, and you cannot talk about water without talking about food. And so the climate issue, the climate problem is very strongly related to water security and food security. And the reason for that is very obvious. We cannot produce food without water. And actually, the basis of food production is, of course, the availability of some key natural resources. We need light for doing photosynthesis. We need, of course, appropriate temperature for proceeding, for continuing with the food production, with the vegetation production. And we need, of course, water, because without water, nutrients cannot be transported towards the biomass. And if you look to the way how these natural resources are distributed at a global scale, we see actually that it is very unevenly distributed. So we have a very heterogeneous distribution of availability of water, or limitations of water, limitations of light, limitations of temperature at a global scale. But we see also that where water issues becomes very constraining for food production, for vegetation production, it is also in regions that are densely populated in the Middle East, in Asia, in Australia. So you'll see that there is a lot of issues where there's a shortage of water in regions which are very strongly populated. Next slide, please. And so another element, what you need to keep in mind if you would like to sustain food production, and food production is, first of all, always based on crop production, that if you would like to produce 1 kilogram of dry matter, that you need nearly 1 cubic meters of water. So this is huge. And so if you have, of course, shortage of water, and we predict that there will be shortages of water throughout the world in changing climate, then this will have, of course, serious impacts on the global food productivity. Now, predictions are made by IPCC. So IPCC, they develop scenarios for different economical evolutions and climate evolution, and they translate this kind of climate change scenarios also on impacts on the hydrological cycle, for instance. And so, for instance, in this figure here, you see what have been published by IPCC in 2023 for different climate change scenarios of 1.5, 3, and 4 degrees. And it illustrates how it will have an impact, of course, on temperature change, but also on critical issues for crop production, like soil moisture. So in the second graph, you see clearly that, well, if we will have climate change, then we will expect that in the nearby future, we will have also changes of soil moisture, which is, of course, extremely important for producing crops. Next slide, please. And so with impact models, crop models, we can translate this climate change scenario in hydrological change scenario, and we can translate the hydrological change in food production change. And so, for instance, in this map, we, not we, but the IPCC compiled informations on the impact of climate change, for instance, on predicted maize production, which is important for animal breeding and other issues. So we see that the impacts are always important, and this is, of course, creates a serious problem for the food security in the nearby future. Next slide, please. Now, in order to illustrate that a little bit further with research that we have done in our team very recently, so IPCC is compiling data at the global scale. We try to look more in detail what happens at the local scale or the regional scale. We were involved in a study studying the impact of climate change on food production in Central Africa, because Central Africa is subjected to a lot of geopolitical pressure. There is a lot of insecurity. There is a lot of food insecurity. There is a lot of other problems with security, and of course a lot of problems with local population. So we try to see to what extent droughts and climate change has an impact, for instance, on crop production, on vegetation production in general. So if you look to the maps there at the top left-hand side, you see the topographic map. So that means that we have a very strong change of topography. We have the mountains in the central eastern slank, and then we have the big basin of the Congo River. And so at the right-hand side, top right-hand side, you see the land use, which is mapped from remote sensing data. You see that we have a very heterogeneous area there. So this region is very interesting to study the impact of climate change, because we have a lot of variability in terms of topography and land use. And so if you, next slide, please, if we look to the way how the droughts has an impact on crop production or in general, we are using indicators which are inferred from remote sensing data. And so what we see in the top figure, for instance, these are figures which are related to climate alterations, everything which is so for the last 20 years, so since 2000, and so this is for a time series of between 2000 and 2024. So what we look at here is how strongly drought events appears, how strongly wet events appears, and how it is related to crop production. And so in the top figure, the blue dots represents wet years, wet months. Everything in red is dry months, and everything in green, the green curve, is actually showing an indicator of the greenness of the whole region. And in the bottom figure, we see actually a range of climate indicators which are related to the global climate system, in particular related to the appearance of El Niño and El Niña events. And so what we can see actually, if you go from left to the right in this figure, is that the intensity of the climate alteration seems to increase very strongly, so that the very dry periods seems to increase from the 2010 onwards. And so also the intensity of the global climate indicators seems to increase. And this has also an impact on the vegetation index in green. It is not so clear, but if you go to the next slide, well, let's say the next slide once more. So if you go look, next slide, yeah. So if you look, for instance, for different crops, how these NDVI index is changing in the last 20 years, as well for grassland, cropland, shrubs and forest in this region, we see that the trend is going down. So that means that the climate alteration at the regional scale for the whole region of Central Africa is actually very significant, and we have a trend which becomes very, very problematic, which goes down, which will have, of course, also an impact on cropland and crop production. Next slide, please. Of course, so in order to handle this, we can propose already a solution, and irrigation is, of course, the strategy that we can develop to face this challenge of global water shortage in the agriculture sector. And so that's the reason, no, the previous slide, please. That's the reason why if we look to the global water use, 69% of the global water use is used by agriculture. 20% actually of cultivated area is under irrigation. 40% of the total agriculture production is done in irrigated agriculture, and 60% of cereal production is done in irrigated agriculture, in particular for rice production, and we will come back to that later on in the webinar. Next slide, please. So if we look to irrigation, there are different ways to do irrigation. We can do it with surface irrigation, sprinkler irrigation, and drip irrigation. In general, these are the large categories, but all these types of irrigations have different efficiencies. And so if we can work on these efficiencies, then we can, of course, increase also the irrigation efficiency. So if we look to the productivity of irrigated agriculture, we can demonstrate, there are figures who shows that the productivity, the food security increases with 1.8 to 2 times the productivity in rain-fed agriculture. In terms of water use efficiency, surface irrigation, which is the most used type of irrigation, has a irrigation efficiency between 40 and 60%. That means that 40 to 60% of the water that is applied on the soil is actually transpired by the plant and is used to create biomass, which is, of course, reasonable, but still very low if you compare it to drip irrigation, where you can have a much more efficient way of applying water to the plants. You are only using water and irrigating water in the root zone of the crop. Next slide, please. So irrigation is the crucial motor that sustains food security at the global level now. And it actually shows that if you look where irrigation is particularly developed, so Asia is, of course, Asia, Europe, and the United States, or regions where irrigation is strongly developed. But there is still quite some potential for developing irrigation, in particular in Latin America and Africa, where also climate alteration becomes very important. Next slide, please. And so some predictions are made by the FAO and also other studies that you can consult in the literature, which shows how irrigated agriculture will evolve as a function of time. So in the nearby future, the irrigation surface will still expand, and the global irrigation volumes that will be used, so the freshwater volumes that will be used for irrigation will also expand in the coming years. And so this is something that we need to integrate in the reflection when we deal with climate change adaptation. Thank you. We don't hear you, Xiaofeng.
Yes, thank you, Marnik. It's my turn. After agriculture, you have noticed that about 20% of water is used by the industry, and one of the main industry that consumes particularly a large amount of water is the power generation. You have different ways of power generation. You can use oil, coal, nuclear, and many others. But what you can see is that any of them will consume a lot of water. Like if you even nuclear power plant consumes approximately 2 cubic meter of water per megawatt hour power generation. And of course, geothermal they will consume a little bit more or less, and the photovoltaic less, and wind power as a renewable energy they don't consume that much water, but only during the fabrication. And of course, the biomass consumes quite a lot because it is linked with agriculture. You need to grow plants to produce biomass, and the hydropower is another thing, consumes a lot, but the water is kept, and the quality is kept as well. So here you have two images of nuclear power plant in the EDF in France, and another gas power plant. But both of them you can see water linked, so they rely heavily on the water cooling of their plant. So let us focus a little bit on the nuclear power, which is quite a bit impacted by climate change and water shortage. It's that it is, as I said, it relies on the water cooling to generate power. However, especially in France, many of the nuclear power plant are not next to the sea but next to the river, and so they rely on the river flow rate and the river temperature to generate the cooling for the nuclear plant. And you have a very strict regulation on the use of water cooling, natural water cooling for such applications, like the temperature cannot exceed a certain value, which is in France is about 23 degrees. So that means if during summer, when the temperature is already quite high, then you cannot rely on this water for cooling anymore. And another thing is about the flow rate. So if the flow rate is quite low, then you cannot rely on the water to cool enough the power plant. So you need to reduce the power plant regime, or you need to stop. Sometimes you need to completely stop the power plant, and that is quite problematic because it's in summer that people probably will need to use their air conditioner. So when they use air conditioner, they rely heavily on electricity. So if the nuclear power plant cannot operate during this hot weather, then you cannot you can have this overheating problem, especially in urban area. So one of the interesting thing that is also linked with the water cooling is the district cooling network. So here I show you a map of Paris, and I show you the district heating, not heating, but cooling network that is available in the center of Paris. So this huge district cooling network, which is around over 100 kilometers long, that cools a lot of office buildings and commercial buildings, and this one is cooled by the Seine River. So as the same, quite similar with the nuclear power cooling issue. So when the Seine River flow rate is low and when its temperature is high, then the production of cooling from water will be in danger. So in that case, the cooling production will rely not only on the water cooling, but air cooling. That means the whole production will generate or release even much more heat in the air, which will make the city even hotter during summer. So this is also impacted by the water shortage issue. Another very recent phenomenon is about the using of artificial intelligence, AI. A study said that in average use of ChatGPT, about 25 tokens. Each time you make a demand, it's a token. So in average, you need 10 to 20 tokens to resolve a simple question. So this use of ChatGPT will require roughly a bottle of half a liter fresh water. So how is the water used? You know that artificial intelligence rely on the calculation, and calculation is about electricity consumption, like your computers. So the only thing that is you have 1,000 of computers or CPU that is or GPU that is operating, and so that consumes a lot of power. And generating this amount of power will consume water, like I said, in the nuclear part or some other power generation plants. And the other part is that almost the whole part of electricity consumption will result in heat. So you need to cool the processor, and cooling this processor will also require water. So that is why the use of AI consumes a huge amount of water. There's another controversial project from Google that was not established finally, is that they would like to construct a data center in Santiago in Chile, but its water consumption per day is equivalent to the whole year water production of a small city, a huge city of 80,000 inhabitants. So that is a huge amount of water that is consumed by the artificial intelligence today. So this is quite recent. And now we will try to see the challenge on the hydropower. So I will hand the micro to Đorđe.
Thank you, Xiaofeng. Hello to everybody. Yes, what we can see from the latest slide, please use your head, not ChatGPT, and drink water. So please, yeah, this could be a conclusion from that, yeah. So, well, yes, hydropower or hydroelectric power is one of the oldest and largest sources of renewable energy, and it really has a long tradition. It uses the natural flow of moving water to generate electricity, and it is easy to obtain and widely used. So please, could we go to the next slide? And in a few points, facility comes in all shapes and sizes. We would like to say that hydropower plant, we usually say it is a custom-made electropower plant, and we should really think how to design it to have a proper fishway, to have fish-friendly turbines, to have to use really in an efficient way these machines, so we can use the water in an efficient way. In this way of production, the electricity, we can say that we really preserve the water. So we just need to accumulate it somewhere, or in some cases, you don't have even to accumulate the water. You can just use it in a flow to produce the electricity. The second point, we can just please go back to say that hydropower plays a key role in keeping the electricity grid stable. It is very important for that, especially pump turbine hydropower plants. The third point is it is an affordable and sustainable green source of electricity. And what we can say as a conclusion, it has relatively low costs throughout the lifetime. So usually and typically, they last for about 65 up to 85 years. What we expect now, they will last even longer. Types of hydropower facilities, they are impoundment, what we can see on the left figure, diversion one, what we can see on the right figure, and about the pump storages, we shall talk a little bit later. Well, when we are talking about hydraulic efficiency, we should always preserve in mind the idea about the efficiency rate of the whole hydropower plant, and one of the main parts of that are impellers. So the types of hydropower turbines, there can be a reaction or impulse. So you can see that these type of turbines that are shown here, they are Kaplan, invented in 1919, then after that a bulb turbine, and one of the designs that was developed at our chair is in the down right corner. So this is the type of the bulb that was developed in our department. It is a turbine with not such a high power, but could be used in micro hydropower hydraulic turbines. Then we have a tube type, straw flow type, and very interesting Francis turbine, invented in 1849. You can see that all these dates are pretty old, so you can see the hydropower generation is pretty a traditional branch of science and engineering. So you can say that 2/3 of all installed impellers are Francis turbine impellers. And of course, we have a kinetic or free flow turbines. Next slide, please. The second big group of turbine impellers are impulse turbines. The main one is a Pelton, and the second one is a cross-flow turbine, very interesting. It has a pretty good efficiency rate in a wider range of the flows, but not such a high efficiency rate in maximum. So this is the model that was designed in our laboratory, and it is also in the production. One of the institutes here in Serbia manufactured this after the design of our department. So please. So what I have already mentioned, Europe is, you can say it is the cradle of hydropower. Well, approximately 135 years, these modern types of hydraulic turbines are in use. However, it's a pity that the biggest hydropower plants, what we calculate here, these are the hydropower plants installed with installed power above 3 gigawatts, are not in Europe, mainly in China, Russia, or United States. The first documented water wheels, you can see that they are dated 2,500 years ago. So people wanted always to use the power of the river to do some work and to help them, not only by watering and for drinking, but also to produce an energy to do some work. What is interesting is the Archimedes screw that was invented about 200 years before Christ. This design is still in use. You can see down there that these Archimedes screw end pumps and turbines are still developed and in use widely all around the world. Next slide, please. So the theory what comes behind all these turbines is the first theory that was invented by the German doctor and physicist Johann Andreas von Zegner. He invented the Zegner water wheel, and you can see this water wheel still in use in different applications today. And after that, Swiss mathematician and physicist Leonhard Euler come up with the turbine equation in 1757. We still use it in unchanged form. It is really, really strange that after all these investigations and all what we have today in turbo machinery, very famous equation made by Euler is still in use. Of course, next to this equation, we have a Bernoulli equation, what is one of the most important in fluid mechanics. You can see here that electricity from renewable sources reaches 47% in 2024 in Europe. So Europe did a great job about improving the import of the hydro sector. And you can see that wind is even more than hydro. So wind is about 39%. And hydro is around 30%. So it is very important because hydro, especially power pump turbine plants, they can be used as a giant batteries. They are very important to be combined with the wind turbines. Okay, please, next one. And what we can see, these are the marks for the 2024 generation by hydropower. was pretty good one. It is 680 terawatt per hour. So installed capacity, that's the number, and also pump storage installed capacity in 2024, we reached this number. Okay, and it is very interesting that in 2024, pump storage capacity added are 187 megawatts. So it means people realized, okay, we can use these, we can say, giant batteries to store the energy, and especially from the wind turbines, and then we can use this energy when we need it. So these hydropower plants are very important in the electricity systems. Please, to the next slide. And you can compare this also with the data from 2017. So you can see that there is an increase in the hydro sector and also in all renewables in Europe in the last 7-8 years. Please, we can go to the next. So what the case about the Serbia? We have 16 hydropower plants with 51 units and about 3 gigawatts of installed hydropower. So it is something close to 37% of total electro potential of electropower. We have a pretty good and long tradition in hydropower. So 120 years ago, the first power plant under the city was installed in Western Serbia, and it started working in 1900s. So what is very interesting on this point is that this is the first hydropower plant in Europe, and only 4 years after the hydropower plant at Niagara Falls that operated on Tesla's multi-phase alternating current system. On this figure on the left side, you can see the monument dedicated to very famous inventor Nikola Tesla, that yes, he invented a lot of things concerning electricity. He was born in the family of the Serbian priest, and after that he made a great success in the United States afterwards till the end of his life. Okay, thank you. The next slide. What we can see here is the biggest hydropower plant in Europe. So Đerdap 1, usually called Iron Gate 1. It was first synchronized in 1970. So when we are talking about the sizes, this is the biggest one if you do not include in a decision and analyzes the hydropower plants that belong to the European part of the Russian Federation, then this is the biggest one. So this is made in the gorge on the river Danube, eastern Serbia, with 6 Kaplan units from our side and another 6 Kaplan units from the Romanian side. And so altogether we have more than 2,280 megawatts installed in this hydropower plant. So it is very important not only for the energy production, but also for the preservation of the water, then for having safe trips for the boats. We can say that Iron Gate 1 and Iron Gate 2 are on the Rhine-Danube corridor, and they belong to the biggest navigation locks in the world. So this is very interesting for them. Okay. And what I wanted also to show that from the mountain region, where we have these very fast rivers, but also very clean ones, you can see on the left side Bajna Bašta from Western Serbia. It is a combination of 2 plants in one place. This big lake, this reservoir, there is also a dam over there with installed capacity 4 units times 105 megawatts, and they are in work since 1966. And after that, on the lower right corner of the left figure, you have also pump storage hydropower plant. Maximum power in turbine regime is 640 megawatts, while in pump regime 620 megawatts. It started operating in 1982. On the right side, you can see the building with the units and the main part of the hydropower plants. So at that time when it was built, the Brutofall was the biggest in the world at that time when it was built, this pump storage hydropower plant. Okay. And why they are very important? during hours of low energy demand. So the water could be pumped from the lower lake up to the upper lake, and then after that used when you really need it. So during periods of high energy demand, water from the upper basins is released back into the lower basin. While in transit, the water flows through the turbine, converting mechanical energy into electricity. So this is one way, very efficient way. Usually efficiency rates of this conversion comes to the point of 70 up to 80%. So what are the advantages of pump storage power plants? They are high energy efficiency. You can use it as a big battery, as I mentioned, the energy storage, flexibility and stabilization of the electrical grid, very important in combination with the solar or wind power generation, reduction of CO2 emissions, and energy resilience. Please. And what I can say in addition to these power pump turbine power plants, so the left figure shows the open loop pump storage. So it means you have a lower reservoir, but the river comes and there is a dam on the way of the river. And also you have upper reservoir. On the right picture, you can see that you have a lower reservoir without river comes in it. So this combination of two reservoirs up and down with preserving the water in them could be widely used even in the case when you don't have a bigger rivers. So what we can see on the next slide is that situation. So the largest pump storage hydropower plant in Europe is Cortes La Muela in Spain. The first phase finished in 1988 and the second in 2014. Now they are preparing also the third phase, and it really has a huge capacity. It has two reservoirs up and down, and you can, in the pumping mode, it can go and use, in that case, they use 1,293 megawatts in the pumping mode. You can visit also this web page on that. And in addition, tidal power is very interesting for the countries with the seas on the sea coast. So what we can point out here is the one, still it is huge tidal power electricity plant. It was built in France in 1966. It is still the second biggest in the world. And it is very interesting because this results in periodic changes in sea levels varying as the Earth rotates. So these changes are highly regular and predictable due to the consistent pattern of the Earth's rotation and the Moon's orbit around the Earth. So they are very reliable, and you can produce really in a good manner hydropower electricity in these places. Okay. And now we shall discuss about the adaptation measures and energy engineering opportunities in this sector.
Yes, well, if we go to the agriculture, food production sector in relation to water, there is a lot of things that can be done. Of course, if we are dealing with the food production sector, we are dealing with farmers. Farmers, they are distributed in regions. They need to adapt. They need to take measures in order to increase their production. So that needs not only technical solutions, but it's also solution with the way how land use is managed, how environmental issues are introduced. So that means that we do not only have to do technical engineering work, but also institutional engineering work. We need to work on legislation, on rules. And so actually adapting as well on technical issues and as well as on non-technical issues, dealing with institutional rules, instruments and things like that. In the next part of my talk, we will not discuss these institutional issues. We will mainly look to some technical issues related to the agriculture issue with relation to climate change and the solution. One of the strategies that can be followed can be regrouped in the term of climate smart agriculture. Climate smart agriculture is agriculture done in such a way that it increases or maintains the food production. So it maintains the biomass production in alternating and in changing climate. It is also done in such a way that it takes into considerations the challenges that are and the constraints that are imposed due to the climate alteration, the fact that the seasons will shift, that there will be much more drought, that there will be much more flooding, that the extremes will change. So we need to adapt so that we can have the capacity to irrigate and things like that. And climate agriculture is also done in a way that it contributes to the mitigation of the climate problem. And I will come back to that later when showing you some issues related to rice production. Next slide, please. In a report that was produced by the World Bank very recently, they actually showed how in different regions of the world, climate smart agriculture can be developed. And there are different options to do climate smart agriculture, but I will focus mainly on some examples of how water management in the agriculture sector can be introduced. And so we are going to illustrate, for instance, issues related to rice production in Asia or in North Africa, the use of water-saving technologies, the use of other issues. So there is quite some scope. So in this slide, everything which is highlighted in yellow shows options that can be developed at a global scale related to water management in the agriculture sector to adapt to climate change alterations. Next slide, please. And so I would like to illustrate this with work we've recently done in related to rice production. Of course, rice is a very important crop. So currently more than 3.5 billion people are using rice as a staple food. It maintains livelihood for more than 1 billion people. But what we also sometimes forget about rice production is that it is also very vulnerable, of course, to climate change because it's a very huge consumer of water. But it plays also an important role in, for instance, biodiversity, because when using irrigated, flooded irrigation in rice fields, then we have, of course, wetlands, which can also contribute to other challenges related to climate change and biodiversity. But there is also the issue with respect to methane. So within agriculture, we are transforming, we are producing biomass. Biomass is, of course, organic carbon that is accumulated in the biosphere. If you're producing this organic carbon in anaerobic conditions, then you can create in certain conditions methane, and methane can be emitted also from rice fields, and 25% of the methane emissions at a global scale is actually coming from rice production. And methane is also a greenhouse gas, which is much more stronger greenhouse gas as compared to carbon dioxide. So that's the reason why we are actually looking very often also to rice production. Next slide, please. And so one strategy that we tested very recently is, for instance, the way how we can produce rice in, let's say, rain-fed conditions or less irrigated conditions. And so one of the strategies that we try to analyze is to see to what extent we can do rice production when doing intermittent irrigation. That means that we are not going to flood rice continuously anymore in the field, but we are going to do it in a discontinuous way, in such a way that during some periods of the crop production cycle, we let the soil dry. We do not irrigate. And the result of that, and that's actually what we try to look at, is that we would like to maintain with this type of strategy the similar productivity and to reduce, of course, methane emission because there are less methane that is produced. And then, of course, we are consuming less water. And another advantage of this type of strategy is that being in more aerobic conditions, we will also maintain arsenic. In a lot of regions all over the world where rice is produced, there is a lot of arsenic that can be mobilized when it is reduced. And that can contribute to contamination of water resources, and that's also a problem. So we try to see to what extent this alternating wetting and drying is an appropriate strategy to increase dramatically the water productivity in the rice production sector. Next slide, please. And so, for instance, what we have done is, first of all, looking to a kind of a meta-analysis. And so in this figure, you see a figure where we analyze the impact of different alternating wetting, drying, irrigation systems in rice production systems will have an impact on global yield, rice production, so dry mass that is produced, but also on water productivity, which means the total amount of water that is used per unit of dry matter that is produced. And so we see in this figure, for instance, that for different regions in the world, but also that actually everything which is right from the dotted line is indicating an improvement. Everything which is on the left of the dotted line indicates degradation. But we can see that there are these kind of alternative wetting and drying strategies which maintains the crop productivity but increases dramatically the water productivity. And it is in a logarithmic scale here, so which actually shows that if you do this kind of strategy, you can improve the water productivity. So that means that you consume much less water while maintaining also the crop productivity. So which is a very interesting strategy. So this is based on the overall literature research about a meta-analysis. Next slide, please. Okay, next slide. This is again done for Xiaofeng.
Yes, still focusing on the plant issue, not in the agriculture, but in the urban area. I just said that in the urban area, the problem is that the pavements are all filled with concrete, so they are not they are not allowing water to go through anymore. So they lose the ability for evaporation. So they're not humid in permanence. So the cities are getting hotter and hotter. So one of the adaptation measures is to put some more green areas in the city, like this one on the car park, and so that you have some vegetations on that. So these vegetations will be able to make water storage during several days, even more. And so to keep the also to keep the whole cities cool, and you don't need to make irrigation very regularly or consume fresh water in competition with other critical water consumption sectors. So if this is an example of how to integrate vegetation on the building, not on the pavement, but on the building, the vertical way. So this is the Museum of Quai Branly in Paris. And of course, you need a lot of maintenance on it. You need to keep an eye in permanence on about the watering, but it allows, once again, thanks to the evapotranspiration, it allows the cooling of the society. So it avoids the using of air conditioners in summer. So it releases indirectly the pressure on water consumption. So one of the other story with the big infrastructure like this one is a huge water reservoir here in the center of Paris, which is equivalent to the volume of 20 swimming pools. So it's huge. So what is the purpose? The purpose is that during a strong flood, a strong rain episode, so if you don't have this reservoir, so the wastewater pipeline could be overfilled, so that you have the mix of rainwater with wastewater. So they will both run to the same river instead of going to the wastewater treatment plant. And that means the Seine River is not clean anymore. So last year during the Paris Olympic Games, during the preparation phase, they constructed this big reservoir. to be used during strong rain episodes. So it's this reservoir that allowed the swimming competition to be held on the Seine River last year. So you also have this type of artificial reservoir for some big or huge cities like here in Paris. So I will give the micro now to George once more about the hydropower.
Yes, okay. Thank you, Xiaofeng. So what we expect in the following years, the refurbishment is in years to come and increasing the efficiency rate of all the hydro power plants in Europe, what we can be sure to be done in the following 10 years. Then involvement in hydro systems, optimization of artificial intelligence, but in a smart way, not always asking and getting the answers. What we are working together with the universities from Europe on this, and also with the universities from China, with the Jiangsu University, with the National Center for Pumps with them. Also, effective and successful adaptive water risk management requires the following issues. So the governance, agency policies, rigorous science monitoring and modeling, and structured and decision-making. So this is very important to have. So in this case, we shall have a flood forecasts, adaptive river and groundwater management. I have left here one reference that people can go and check different things, yeah. Yes, and poorly managed water, it is really an issue all around the world, and there are a lot of things that could be improved. We have seen some examples of improvement in France that Xiaofeng told us, but what we face, we don't have enough water. So for drinking and so on. But in the second case, we have a lot of water, so during the floods and so on. And the third issue is water pollution. So how water is mismanaged in Europe, you can see in these slides here. And you can see that almost a quarter of treated water is lost during distribution. In some countries, I can testify it is even bigger than that, so double that. So it can reach up to 50%. So you have a prepared water and you don't have a good distribution network to go to the people where they have to drink the drinking water. Yeah. Okay.
Yeah, so there are also some very fundamental innovation in terms of water, especially in some critical areas like islands where you don't have enough fresh water for drinking. So here I show innovation of dew harvesting, dew with the humidity or moisture that is in air. So with this thin film, so we're able to collect half a liter or 1 liter, up to 1 liter per square meter per night. So it mainly works during the night, thanks to radiative cooling. And we also have some more performing device like this one developed by MIT scientists, but also some European scientists working on MOF. And using this MOF material, you can collect even more water during one night, and even for some situations, even during the day when you have solar radiation. So the innovations are underway as well. So if you are interested, there is some artificial management of the underground water, which is similar to the reservoir that I showed you in Paris, but this is in a much higher or larger scale on the aquifer. So you have this alternative filling. You have some policy or other measures that you can use to preserve the availability or the capacity of water returning of the groundwater. And it just appeared on the Science magazine in March 2026. So I will give the last slide, the last quite particular one, a recent one, to Đorđe, who's talking about the situation in Belgrade.
Yes, thank you, Xiaofeng. Well, students and academic institutions in Serbia, together with the citizens, are fighting for more than 17 months in Serbia against the corruption and also including the various water protection issues. You can see that mining is a great issue in Serbia, like the exploitation of the Jadar Valley lithium borate deposit in Serbia by the Rio Tinto Corporation. In this place, we have a huge water reservoirs, and they want really to destroy that just because of the mining. So all our students, together with the professors and the citizens, fight for that. And here is the sign of our, on the right side, you can see the sign of our students from the Faculty of Mechanical Engineering, and you can see the translation. So machine engineers against the machinery. So machinery is a regime that wants to spoil and the land and the water and swims in corruption. So this is on the left picture, you can see a huge number of Protestants that we have. So more than 300,000 people in the streets. What is happening nowadays, I will send you one link. This is the link that we got yesterday from the Circle U. So Circle U comments and give a statement about the recent developments in Serbia. And there is a statement from our rector of the university, what is really going on and how the students and the citizens and also the whole university are under the pressure of the government because we are fighting for the water, air, and the land and against the corruption. So please, if somebody can read something, please join. But this is a social impact of the research, and how to preserve the country for the upcoming generations is a part of this fight. So thank you, Xiaofeng.
Thank you, George. We all feel concerned about the situation. So we're together with you and your colleagues and students in Belgrade. I hope that situation will get better soon. So this is the end of this webinar. I didn't check the time, but I hope that we are on time. And now is the question and answer or discussion part. I